All right, so right, we recorded. Nice. Let's go. So right, if the AC currents, AC alternating currents can be represented alternating, right? Alternating currents can be represented by the following sign graph, right? So on the sign graph, we have current and we have time. Oh yeah, sorry. All right, so what you say? So what you have, right, is you have current versus time, and you have a sign graph, right? Zero, maximum, back to zero, negative, so on and so on, right? What you will recognize here is that some of the values are positive, some of the values are negative, right? What do we call this here? What do we call this value here? I naught. What do we call I naught? What do we call I naught? Max value, okay. But we can also call it peak value. So the peak value is I naught, right? But if we go from here to here, if we go from I naught to minus I naught, we call that peak to peak value. We call that peak to peak value. Everybody okay with that? Atilia, what is called this value right here? Very good. Period. Right? You call that value period. Time for one cycle, right? And then what frequency again? Frequency else? Very good. Frequency else 1 over period, measured in hertz, right? So the frequency is given by that. Wait, stop talking now. This is so yeah, I need to Right, yeah. So the question I'm going to ask is, what is the formula? Well, what do you think the formula will look like when you all reach here? Hold on. When you all reach here, I is equal to what? Set, set, yes, set.
I was gonna ask you no question. That's the one.
I saw who set. Right. So, right here, the question I was asking, what is the form? What do you think the formula for this to look like? I is equal to what? The sine graph, right? So sine should be there. It must have a magnitude. The magnitude is the biggest value, which is I naught and theta, right? But you may not remember, but omega is theta on t. So theta is omega by t. Anybody remember that from simple harmonic motion? Yeah. What's omega again, Olivia? Omega is also what? 2 pi f. 2 pi f. So it will be 2 pi f by t. Okay? That is your equation generally. Remember, it could also be the same thing for voltage, right? V is equal to V naught sine 2 pi f by t. Okay. All right, next. Yeah, what were then? You get you? All right. So how do we sketch something like this? Jacob, how do we sketch a graph that looks like this? Huh? So we need a peak value, so very good. It's a sine graph, nice. What else we need to sketch a graph? We need the amplitude, we need something else. Period. And period is how much? 1 over f, period of t, right? So it's 1 over f. F is how much? Okay, let me make it even. F is how much? 2, right? Because 4 pi should be equal to 2 pi f, right? So it means that if 2 pi f is equal to 4 pi, f is equal to 2. So the period is equal to 0.5 seconds. Everybody okay with that? So now we can sketch it. We know how high it's going. We know how long one cycle is. And you good to go. All right. I mean, okay with that? So excuse Darian. Suppose I give you a graph like this now. Can you get the formula? Okay, can you do the reverse and get the formula? Yeah, if I give you something different. Yeah? All right. So what I'm going to do is touch up and do that. Oh, I said out loud. Sorry. I was thinking it. Sorry. Oh, I was tripping now. All right. Right? Right, the formula there from up. So do in the reverse of what I just did. Take this graph and write the formula. Online audio, okay? You're done? You're done? Now you're gonna go watch. Right, let's go. Faith, help me out here. What's the peak value, Faith? 3. What is the period? So the frequency is how much? Huh? 5. How you get that? So tell me what the formula is. I is equal to? Five, you sure? I thought it's 2 pi f. So it's 2 pi by f. 2 pi f. Okay? So I is equal to 3 sine 10 pi t. Right? So the formula for this is this. Formula for this is this, right? Nice and simple, right? But the problem is, if we do have time, we can't get the current value. So we have to find RMS. Right? Yeah, very good. Yeah, average. Leads to it. Right, guys, it's done after. Since one alternating current, since one alternating current, its magnitude is always changing with respect to time. Its magnitude is always changing with respect to time. We need, oh, sorry. Its magnitude is always changing with respect to time. We need a single value. We need a single value within brackets average. Within brackets average. A single value that can be used in place of this alternating supply. In place of this alternating supply. Full stop. This value is called the root mean squared. This value is called the root mean squared. And it is the DC equivalent, DC, and it is the DC equivalent. It is the DC equivalent of the alternating supply. It is the DC equivalent of the alternating supply. Right? So IRMS is equal to sometimes they use 0.707 I naught, or to not round off, they use I naught on root 2. Just a second, the one on root 2 there. 1 on root 2 is how much? Okay. No, I wanted to make sure I was right. Is that correct? Yeah. Yeah. Right, so your RMS value is that, right?
All the time.
Yep, all the time, all the time. But is that proof? Like if you prove it and do the integration, you'll get it. So your RMS values are what you're using in calculations, right? Hey, what is the quiz up, Chris?
26.
Huh?
26.
That's it? 26 up? Alright, look at that question there. Y'all seen on the screen? Alright, I'm not sure why the question, I'm not sure. Just no, I'll give her one second. Alright, I'll try and fix that up. We have a back way. Right, so that is how you find it, right? And then power is what? Or do you remember your little current formulas?
Yeah, forwards and
No, in terms of Darian. Power is what? Picking on you. Darian. Power is what?
Wash. Oh, right now.
See why? I'm gonna show you something here. What is power? Power is what? In terms of electricity.
Yeah. Power is.
P is equal to power is what? I by V. Or power could be I squared R. Right? So let's just make a note of those two now. You might need them later on. Alright, so right, hold on, I'm back in there real quick, right? Sure. Tyrese. Selena, Kiran, Shazana, Faith, Seth, Daniela, Reese, Darian, Yash, Judah, Katrina, Vinay, Renzo, Atilia, Nathaniel, Eden, Jacob, Rian. All right. So let's take a look at how we can do it easy, and then I'll come back and look at it. All right, so before, right, I'll give you a question. It's not a little while, right? But let's just explain that first. I'm not sure why this screen not coming up from a phone. Right, what you see? So I just reviewing this quickly, right? Sylvester, go start him now, please. Watch here. You gotta remember what this does? Diode, yeah. What does diode do? Yash. What I mean? So if I give you an alternating supply and I connect the alternating supply to a diode. One diode to that pair. So your supply here is what? Looks like this, right? Alternating, right? Oh, you Google that password. Right? So if I put a diode there, if I connect that diode to the alternating supply, what is happening? It's made the current go in one direction. This is happen. Conduct here, do conduct here. So it'll look like that. And it looks in form 5. That's called what? Half wave rectification. Yeah, we got the whole thing today. Right? So a diode, one diode will do this here for you, right? Yeah, listening.
So when you do that, right? You have periods of time where no current is passing.
Right, so that useless, right?
Yeah.
So what we're gonna do now is do one that allows current to go flow all the time. Yeah, that's full wave and then the student is back. Right, so here we have this diode. This is the pump 5 stuff. Right, today we're gonna do the unit 2 parts of it, right? P2 goes. What's the talking now?
Yeah, reflux it. You can sign this with now. Paper one. Sir.
Right, yeah. I just doing wrong now. How you connect this up now? I wanted to make sure it worked out proper. A, B, C, D, E, F. Right, so down there, may I explain it? Carry on those. Take your time, right? Must be in that order and that direction, right? Right, we can label them up too. We could call this D1, D2, D3. All right, let's go. You're done? Right, and connect up voltmeter, right? Let's see if we can. Let's see if we can explain what happened here.
Yeah, see, it's more like a mobile man that's what see, it's more of a man that's me. Yeah. They are doing. Exactly. But I just yeah.
All right, let's go. Let's see if we can actually on this as well. So too bad. Picture, they take a picture. Huh? Want to explain? Go ahead.
This is the supply here. And after it comes through this, the output is linear on one side of the plate. No? So, there's M's next to each other. Right. On one. Because when the current passes through, this is negative to no
One positive, one. Let me say that.
convention.
P. Yeah.
Alright. So it come here. When they come here, it's in the positive. But then after it have a gap. So they come here.
Gotcha. That's
No.
but I'll get you. Not bad. All right, let's go. So here's what we want to observe, right? This is called, you ready? This is called half wave rectification. We are going to try to get full wave rectification fit. Okay? Full wave is this. Right? So you want to see how this diode bridge will work, Yash. Right? So remember, alternating means current will go in this direction one time and then this direction. So I am going initially from positive to negative. Right? Let's see what will happen. Okay? Current here. So it's going this way. When it reaches here, can it go down diode 4? No. Because diode 4 is reverse bias. So it'll go down, right? So from P, it will go through diode 1 because diode 1 is forward bias. Now, when it reaches diode 1, it will come to C. When it at C, will it go back down diode 2? No. Because diode 2 is reverse bias. So it goes to D2. You okay with that? But when it reaches, sorry, it will not go to D2, making sure the sharp. It will go through the resistor. It will go through the resistor. You okay with that? And when it goes through the resistor, it will reach up here. See if we can figure out what will happen when it reaches right here. I want to know what will happen.
Yeah.
Right, so watch here. So when it reaches D earlier, when it reaches the letter T, where will it go? It will split. No, that won't happen. It will go to D3. How does current flow? From a high to a low potential, right?
Yeah.
So basically, and here's a higher potential. So it wouldn't go from a high to a high, it will go from a high to lower potential. Current always goes from positive to negative. Okay? So current always goes from high to low. Okay? I should say first cycle here, right? First cycle. Everybody okay with that? So it will move from high to low. So therefore, here's high, can't go up here. It will have to go low, right? So it will go from D to D3 and then to E. When it reaches E, it will come back out there. That's okay? So now, what's happening here? During the positive cycle, all of the current flowing this way. So it means that the voltmeter will pick up this here. That's okay? Current going this way. So I put in a little arrow here, current going that way. Diane, you okay with that? So here's how I try to know Diane. Anybody, I want somebody to come on the board now and tell me what will happen on the opposite cycle. First cycle, first half cycle, and now second half cycle. Right? Same thing, but here what happening now? Down here positive, down here is negative. So it's starting at F. Am I gonna try? No, on the board. Am I gonna try? Lion? I want you to tell me now, current direction change. It's not going from A, it's starting at F now. It switch. So current going this way. So I want you to try now. When it reach F, where to go? Want to try it now? Alright, tell me what to do. Tell me what to do. After what? After E, then it will go through which one? Because D2 is forward bias. When it reaches C now, what will it do? It will go through the resistor in the same direction. You recognize that? It will go through the resistor in the same direction. So although it negative part of the cycle, current still going the same way, right? So it's going like that. Right? Let's make sure. When it passes through the resistor, where it going? It going to D. When it reach D, where it going? No, because remember here's a higher potential. Here positive now. Here, this side. So it wouldn't come back down here. It wouldn't go high to high. It has to go high to low. Here negative. Here's a low potential. Right? Not on the board down. Right? And when it goes to D4, it goes to, and when it reaches B, where will it go? Right? It will go to A. Here's a higher potential, so it wouldn't go here to go here. So basically it's flowing like this. That's okay? So it going to E. Right? So what that means is when it's positive, it's positive. When it's negative, it's positive. When it's positive, it's positive. When it's negative, it's positive. That's called full wave, yeah? Yeah.
So get halfway around application of that was, and then it just like set aside so that
Possible. But what might happen is so it will work for everything. Might work for everything.
So you're struggling.
So he's saying struggling.
Yeah, try it and see now. Find a way to connect it and see if you can do it. But the reason I would have done this is because this should work for every. So technically, if you look at it, it's only two resistors you're using for one cycle. So you're using D1 and D3, and then you're using D4 and D2. So for the first half cycle, you're using these two. We don't care for these. And then for the next half cycle, we're using these two. Right? So technically, there might be a way to use two. But they will have a flip somehow. Something had a flip. So that's why they have this fridge.
Okay. I think I want to folks that we believe so that
Yeah. So that's probably the problem. That's probably why they didn't use it. Sorry, sir?
Yeah.
Oh, yeah. No, once it's the coming here, we talk by mistake. Okay, now. Right. So how do we right? I know I didn't show you as yet, right? But how do we smoothen this out? Right? I didn't teach you about the components you need, right? How we can do this, because the problem is it dipping here still. Huh? Yeah, but how? What we can do to make it straight? Huh? Right, but we gotta add something in here that would allow us to do that. Yeah, component. It's called like a capacitor. Right? Right, so a capacitor, a large capacitor will charge up, and while this low, it will discharge. Charge up, discharge. Right, you can connect it right here. You finish here? Right, just two things I want you to note, right? Online, are you okay with this? Rihanna? Yeah? Katrina, are you okay? Right, just note that all the diodes are forward bias. Note that all the diodes here, these here, all the diodes in here are forward bias. All of the diodes here are forward bias. And the second thing is that must always remember that current goes from a high to a low potential. Right? Two little things I want you to remember. Diodes are all forward bias in the cycle. And current flows from a high to low potential. Current flows from a high to a low potential. Right? So it's really important to remember these two things when you explain it. Under that right is clear. If we connect, you write it. If we connect, Faith, or stay quiet now. If we connect, yeah, surely, right. If we connect a large capacitor, across the diode bridge, we can obtain a straighter graph by smoothing out. We can obtain a straighter graph by smoothing out. Underline the word smoothing. By smoothing out the full wave. Full wave rectified Well. The full wave rectified graph. Hmm? Right, so what is here? I don't want to draw it in this. Ideally, what you have to do is draw over this whole thing, right? But what you could do in a pencil or different color, I mean, you could put your capacitor in here. Right? Capacitor is two parallel lines. Ideally, yeah. Or you could just remember it. But it can't be in the full wave, huh? This is smoothing. Alright, so watch this here. I want to explain how the smoothing works. You ready?
So we've read it over.
No, don't draw over the whole thing. Just take a coloring and just squeeze in the capacitor now and make a note.
Right, so don't raise your head. Marco said they get it you.
Alright, so watch this here. Watch here, Diane, trap now. So watch this here, I told you. Why have a black thing? Anybody have a black? It's black. Correct. Alright, teacher. So watch this here. So I want to explain how we can smoothen out, right? Smoothen out means we do all these lumps here. We want to smoothen it out like that. Right? Here's how the capacitor would work, right? And it must be a large capacitor. So you can store the charge and then discharge. Okay? Here's how it works. When you connect the capacitor, as written on diagram, and then to pay attention. Right? So it will start here and the capacitor will charge. When the capacitor reaches here and its voltage begins to drop, what will happen is that the capacitor charged. So a capacitor, for those who don't know, is a device that will store charge and then give it back. Like a home battery, right? So it will charge when it reaches here and the voltage begins to drop, it will start to discharge. Right? The capacitor will discharge. Then this small area here, it will begin to charge again. When the voltage begins to drop, it will discharge. Although it's not looking perfectly smooth, the bigger the capacitor will smoothen it out because it don't need to charge back up here. That's okay? And then it will charge a little bit, then discharge, and so on. Right? So it's not perfectly a straight line as the other. To get it straight line, you need a capacitor that will charge here and then discharge to the whole thing. So the bigger the capacitor, the better that will happen. Okay? But for now, you need to understand how to go from full wave to sort of smoothing out. This smoother than this, right? No, they can share for a login. Yes, and the whole live. I'm gonna share the crap down up.
So how are you doing this?
You grab light on.
Oh, yeah.
That's not all of it. I don't have my eyes, but I'm gonna find it back.
Yes, that's.
Well, yes, you can just find the end share 2016. 2016. 2016 number 5. You're okay with that? Yeah, you're okay with the diode works, the calibrate works? Alright, so we're gonna try 2016 number 5. So if the class online, you're one of them, you want to benefit your.
I don't like. So,
If I ask a question,
so was it cool for this?
957 372 20116.
Yeah.
548 142.
So,
548 143. Yeah.
Yes.
Esse. E a outra tá. Tá
Arabacá. What time?
93.
Yes, come on.
That's only.
Então, tipo, tá.
That's only.
Você,
So from 93.
e a outra você
It's that kind of
Right, let's go. Right, let's do this before we leave, right? 2016 number 5, real easy. You gotta write in the answer. No, it is easy. With the A-level diagram, hey, Marquis, question, you gotta work out this. Take off this now, yeah. Take off this now. Press the icon. Right. With the A-level diagram, with the aid of a diagram, explain the operation of a simple half-wave rectifier. You can handle that? A simple half-wave rectifier, right? Alright, we'll skip that part out. I want to skip it. Actually, it should go to circuit pass. I'll just stop that now and just join circuit from now.
So you don't understand that.
Hurry up, draw the circuit. Right, the same circuit I gave you all just now. And then draw the output underneath. Hurry up. Wait, are you done? Do the thing fast now. I tell you another time. Let's skip these two parts then. Right, because I just gave it. Or taking too long. Right, do this please. Start here first. Look at some here, boy. Some. Start at fast.
So say talking of which I guess.
Nine something. After 10 is my favorite, so you say.
Jacob, that's the jump in there for money. The way you said. Yeah. 2016, number 5. This is part B. So they gave you the formula 156 sine 314. Find the peak value, the frequency, root mean square. Hurry up. Finish. Huh? You listening?
Yeah, the big equation.
Right, time of peak value is how much? Voltage, right? So 156 volts, right? What is the frequency? 1 over? Right, I think peak value is 156 volts, right? Frequency is, write a period to, sorry. So how you get frequency? No, you have T as yet. No, there's no pi there, that's like 314. So what does 314 equal to? 2 pi f. So write 2 pi f is equal to 314 and then find pi f. Find pi f. 314 what 2 pi. How much is that? Pi 0? Yeah? Okay, alright. I didn't write it. Oh, let's try 50.
So it's 49.975. So it just approximately.
So 314 divided by 2 pi, right?
Yeah.
Okay, next, root mean square. Let this one go to feet. How do you find root mean square? Always do something about that. Right, VRMS. Right, if I write VRMS first, I'm very good. What is that? 166 or?
So how I want to be like that,
No,
What's that? What do you mean?
Right, so this sounds pretty actual. Right, the top one is.
We can have like a picture.
Oh.
And the same thing, I just Lucky, just like you. Yours first.
Wait, the answer.
I'll invest in that card.
The answer.
110.31.
What is that?
0.31 volts. All right, next one.
Next one.
Any questions online?
Yeah, question.
Take a little read now. Draw a labeled sketch. Do not plot. Showing the correct values of the amplitude period for 2 cycles. When this waveform is applied, right, wait, watch it carefully. When this waveform is applied, wait man, right, is applied to a simple half wave rectified circuit. So you have to draw it using the values above to get that half wave rectification. Want to try that? 2 cycles, right? Must have 2 cycles.
Yeah.
2 cycles is just from 2 cycles. That's what 2 cycles is this, right?
Yeah.
So to obtain from 2 cycles, that's really 2
It'll be
cycles. Right. But you went the next time.
Okay, no, I can draw a line, but that was not the same. That's 2 on top.
That's 2 on top. Right? Try it there. Well, stop playing with that now and go and say. Yeah, well, we can stop, but just draw the graph from first. Who has the iPad? Draw the output, please. It's an applied simple half wave. Draw the half wave in Darian. Draw the half wave.
I don't know what you.
How you draw a half wave rectified?
Oh,
the graph. Right, and the one value. Show the amplitude. What's the amplitude? And the one the period. What's the period? And you put it in the right place. We're very good at shop. Huh? 1/50. Alright, that can pass. Yeah, minus take long here too. Like that, longer than that. You don't want to hear any do that. I'm gonna get excuse about it. What's that, bro? I'm gonna get excuse about it. Alright, nice, Olive. Very good. Put in the SI units of volts and time. Volts and time. Just put volts and time. Are you okay with that? Anybody confused with this? Alright. Instead of a little note, we have to explain how the diode works. So your homework is to write a note on how the diode works. Explain doping and thing next time we talk. How the diode works. That's your homework, right?
Say,